Well, see, in the last lecture, we have developed idea how to calculate work in adiabatic expansion and compression, how to calculate delta H, and what is the change in internal energy. Now, see, now we can compare the expansion isothermal and adiabatic, right? And what is the relation between them? We can deduce. So, see, this is very important that if we take, I mean, two different paths, one is isothermal and other one is adiabatic. Adiabatic. So what is the basic difference between these two? In isothermal, temperature is constant, but here there is no constant temperature. So in case of isothermal, gas is always PV is equal to constant, and in adiabatic case, PV to the power gamma is equal to constant. And here T is constant, but here T is not constant. So since T is not constant, so the variation in pressure here in adiabatic or in isothermal, if we compare, then definitely the rate is different. I mean, rate of change of pressure is different in case of adiabatic and isothermal. So suppose we have started with the initial same initial state isothermal and adiabatic. Suppose that we have a plot, and this in this expansion, if we have started with the same initial state isothermal. So if this is the plot of isotherm, then adiabatic is like this. Adiabatic is like this, right? See, this is the initial state, okay? And if you move back side here, so they will cross like this. Right? This is the initial state. So see here, pressure is final pressure we are taking same in both the cases. In both the cases, I am taking final pressure is same. So what will happen? Final volumes are different. So this is the volume for isothermal and I isothermal, and this is the volume for adiabatic. So for adiabatic process, volume is less. Means if you, I mean, if you want the final pressure in both the cases is same, then volume of isotherm is more than the volume of adiabatic, right? Means in both the cases, final state cannot be same. See here temperature is constant, but here temperature is also varying. So difference between this P and V, in this way you can find out. So why I have taken this P and V, although we can take any kind of plot, but P and V, the calculation of work is, I mean, easier for us. So if you see area under the curve, so area under the curve for this isotherm is more. So this is the initial state. So the area under the curve for this isotherm is more this than the area under the curve for this adiabat. So you can say this is the area under the curve for what adiabat. This, right? So you can say from here that W reversible of isotherm is more than the W reversible of adiabat. Right? So work involved in isothermal case is more than the adiabatic if there is expansion. And here final volume, initial state same. Initial state is same for both. Same for both. Right? But final state different. Final state different. Means volume of isotherm is more than the volume of what? Adiabat. Volume of isotherm is more than the volume of adiabat. And if you want to fix volume same, then pressure will be the different. Right? Then what is the relation? When a volume of isotherm is more, means pressure of isotherm is less compared to the adiabat, right? So in this way you can compare adiabat and isotherm. Now see what is the relation between their slope. So all of you are knowing that isotherm PV is equal to K. So dP by dV isotherm T constant is equal to minus P by V is equal to the slope of isotherm. Slope of isotherm, right? And for adiabat, P V to the power gamma is equal to constant. So dP by dV adiabat is equal to minus gamma into P by V, right? So this is equal to the slope of adiabat. So you can write dP by dV adiabat is equal to gamma times of dP by dV isotherm, right? Means gamma into slope of isotherm. Slope of isotherm. So this you can see here. This is gamma times of the slope of this. This is adiabat, this is isotherm, right? isotherm, and this is adiabatic. Right? So in this way you can compare the work, expansion work for any ideal gas in case of isothermal expansion and adiabatic expansion, and you can compare the slope as well, right? Similarly, suppose that if we have different gases, suppose that if we have helium and hydrogen and carbon dioxide, and it is asked that okay, uh, adiabate is given, P and B, right? And suppose that different adiabates were given. Suppose that different adiabates are given. So it is asked, okay, identify which curve, which plot is for which gas. So you just compare the gamma. Gamma for helium is, gamma is equal to 5 by 3 monoatomic. Gamma for diatomic, we have already calculated. 7 by 5. What? See. Uh, for monoatomic 5 by 3, for diatomic 7 by 5, and triatomic linear 7 by 5. So diatomic and triatomic non-linear we can take 1.33, 1.66, 7 by 5 and 4 by 3. Right? 7 by 5. This is 7 by 5. And instead of carbon dioxide, we can take this sulfur dioxide. So this is gamma for this is equal to 4 by 3. Right? So this is triatomic, non-linear sulfur dioxide. So as you, see, the slope of adiabate is minus of gamma. All have negative slope. So gamma, value of gamma for which gas is higher, that belongs to the, maximum gamma value with this, then this, then this. So if we write here gamma 1, this is gamma 2, this is gamma 3. So gamma 1 is maximum, then gamma 2, then gamma 3, right? So identify for which gamma is maximum. This is 4 by 3. So 4 by 3 is equal to 4 by 3 is equal to 1.33. This is 1.33, and 7 by 5, 7 divided by 5, 1.4, and this is 5 by 3, 1.66. So means gamma 1, this is for helium, this is for hydrogen, and this is for sulfur dioxide. So in this way you can determine different gases if slope given. So you just compare the value of gamma and answer the question, right? So we have compared this isothermal versus adiabatic, I mean expansion work, and already I have see here written the result expansion. This is within adiabatic, and this is the comparison of adiabatic versus isothermal, right? Now, see, we can plot a different, I mean, plots for this adiabatic expansion. Suppose that, another plot is asked between T and V. Suppose that here temperature is given and here volume is given, right? So and adiabatic comparison, you have to compare adiabatic reversible adiabatic expansion. So the case is given reversible adiabatic expansion. Adiabatic expansion, right? So adiabatic expansion means volume is changing. So suppose that initial state is here, so I adiabatic expansion, you will get the curve like this. So this is adiabatic reversible adiabatic expansion. This is curve number 1. This is 1, right? And if it is asked isothermal, right? Reversible isothermal expansion. Reversible isothermal expansion. This is curve 2. So this will, the path of this will like this. Right? This is initial state. So this is plot between T and V, right? Here I have given you the plot between P and V. This is between P and V. So this is isothermal expansion, adiabatic expansion. Clear? But if you take temperature versus volume curve, so you will get like this. Now one more is left. Suppose that if we take temperature versus pressure. Temperature versus pressure. Suppose that here temperature is given and here pressure is given, right? And it is I mean expansion. So reversible adiabatic this is T, right? So when we take P versus T plot, so initial state will lie somewhere here, right? And isothermal expansion is like this. The path of isothermal expansion is like this. Temperature constant, and why this is called expansion? Because here pressure is decreasing. Pressure decreasing means volume increasing. So reversible isothermal expansion. This is plot 1. This. And if you take adiabatic expansion. So this plot will I mean somehow like this, like this, right? So this is reversible adiabatic expansion. This is plot 2, right? So in this way, you can explain I mean adiabatic expansion on PV plot, on TV plot, on TP plot, and every point is justified. See here, this is isothermal, and expansion between T and V. So here T is okay, no problem. T is here also same. Here V and here P. So if this point is here, obviously in the pressure P and V are inversely related. So this point will definitely will I mean opposite to this. So if volume is low and T is high, so T is high, volume is low, both favors the high pressure. So pressure should be here high, and pressure is here high. So this point should be like this. So every point you can justify here. So in this way you can explain the different plots for expansion, reversible isothermal expansion, adiabatic reversible expansion on different coordinates, means between T and E, between P and V, between T and V, right? So this is uh, all about the comparison of work, expansion work between isothermal and adiabatic, right? One more case we can develop here, that is a polytropic process, right? Polytropic process. Polytropic process, right? See, this polytropic process is very much similar to this, adiabatic process, but not exactly equal to the adiabatic process. But this polytropic process, through this single equation, we can explain all the above process: isochoric, isobaric, adiabatic, isothermal. All processes can be explained with a single equation, and the equation is PV to the power n is equal to constant. Okay. If any gas obeys this equation of state, then this is called polytropic process. What is n here? N is any real number. Real number, right? So you can take this n is equal to 0, n is equal to 1, right? And n is equal to fractional as well, okay? Any number, but I'm taking some discrete values here. So if you see here in polytropic process, PV to the power n is equal to constant. So n is a real number. So we can make a plot to show this process. this is P and this is V. Right? Right? So see different plots I have shown here. Okay. So this n is equal to I'm in 0 here. N is equal to 0. So if you put n is equal to 0 here, so you will have this, which type of process? Isobaric. Pressure constant. Isobaric. Here n is equal to 1. So this is isothermal. Any intermediate state is also possible here. And n is equal to gamma. If we put n is equal to gamma, so PV to power gamma is equal to constant. So this is called what? Adiabatic process. Adiabatic process. And n is equal to infinite. So this is isochoric. Isochoric, right? So in this way, you can, explain all the above processes: isobaric, isothermal, adiabatic, and isochoric by a single equation, right? So see, for isobaric, for adiabatic, for this isochoric, or for some intermediate steps, when n is not equal to 1, we can derive some formula for calculation of work. So now the next point is to calculate the formula for work. Although we have calculated, but again we can derive this calculation of work for polytropic process, right? Now see how to calculate work in polytropic process. So simple, as we have calculated different work, PdV work, we can calculate this also. See, P V to the power n is equal to constant K. I'm starting with this equation. So at any moment of time along this PV path, we can write P1 V1 to the power n is equal to P2 V2 to the power n is equal to P3 V3 to the power n is equal to K, right? For 1 mole of the gas. Here n is not the moles, n is any real number, right? N is any real number. Got it? Real number, right? So PdV work delta W 1 to 2 is equal to minus P dV, and I am taking reversible process, right? Process is reversible. So what will happen here? In place of P, what we can write? So we can write here minus K by V to the power n into dV 1 to 2. This is equal to minus K 1 to 2 dV V to the power minus n, right? Now we can integrate this. So we get W reversible is equal to minus K by minus n plus 1 into 1 by V to the power n minus 1 V1 to V2, right? So we can write here K by n minus 1 by V2 to the power n minus 1 minus 1 by V1 to the power n minus 1, right? So this equal to, we can write 1 by n minus 1 K by V2 to the power n minus 1 minus K by V1 to the power n minus 1. So here we can write 1 by n minus 1 P2 V2 to the power n by V2 to the power n minus 1 minus P1 V1 to the power n by V1 to the power n minus 1, right? So we can write here 1 by n minus 1 P2 V2 minus P1 V1, right? W reversible. So this is a formula for this work, but n should not be equal to 1. N should not be equal to 1. So this formula is you can use for any type of work calculation except isothermal process. N is equal to n should not equal to 1, because n is equal to 1 is isothermal process. Right? So one more form we can write here: W reversible is equal to 1 by n minus 1, and this you can write delta PV, and here you can write n minus 1. This is equal to, you can write NGR delta T. So this is also a formula for the calculation of work in polytropic process. Now you can modify this formula more, that in place of R you can write CV, Cp minus Cv is equal to R. So we can write Cp by Cv. Okay, not required. Not required to change this. Don't do that. So you have two different formula for the calculation of work here. From equation 2 and equation 3, you can calculate the work involved in the polytropic process, right? But that process should not be isothermal, right? So from equation 2 and 3, equation 2 and 3, we can calculate PV work, PV work in polytropic process, polytropic process, except n is equal to 1, right? So you can calculate this. One more, important formula, that also the same formula, but I am writing here. Heat capacity along any path. Heat capacity along any path. Along any path. So heat capacity along any path C, this is not specified, that is, this is constant pressure, constant volume path. So along any path, right, that is C, is equal to CV plus work. Which work? This PV work. Directly you can do this, right? And this any path means we can choose this polytropic. So we have calculated this polytropic path work. So this work is equal to 1 by n minus 1, right? And ng is equal to, I can take 1 mole into R into delta T is equal to what? 1. Because as you know, heat capacity, if you are going to calculate, so heat capacity is defined per degree rise in temperature. So this is always delta T is equal to 1 degree Kelvin or 1 degree Celsius, right? So this is equal to R by n minus 1, right? So as we know that we are always taking this PV work, minus PV, basically minus PV we are taking here, not minus PV, but this sign is basically minus here, not plus, because you know this formula I have taken from thermodynamics first law basically. So I can write here, see, uh, delta E is equal to delta Q plus delta W, right? So this delta Q is equal to delta E minus delta W, right? Basically, this formula, what equation 1 I have written here, that is on the basis of this. See, Q by T. Q by T is the C, heat capacity. Delta E is NCV delta T, that by delta T. So T cancel, right? So this formula I have written from this formula. And if you want, you can derive also very easily from this. So CV minus this work we can put here, R by n minus 1. So if you want, you can write here CV plus R by 1 minus n. 1 minus n. So this is the formula for the calculation of heat capacity along any path. Any path. So this equation you can use to calculate the heat capacity along any path, right? So this equation we can equation 1 we can write from this, but no need to derive all those things, and much derivation is required for you. So that's why I am directly writing this, right? So this you can use to calculate the heat capacity along any path. This is very important formula, right? This is very important formula. Suppose that question is given, for example, 1 mole of any gas is, expanding or change in 1 mole of any gas, that will follow this path. P by V is equal to constant, right? Ideal gas, 1 mole of ideal gas, 1 mole of ideal gas, ideal gas expanding along this path. P by V is equal to constant. 1 mole of ideal gas expanding or changing, moving along this path, changing along the path for which 1 mole of monoatomic, right? Along the path for which P by V is constant. Constant. Find the heat capacity, heat capacity or specific heat, because 1 mole we have taken, specific heat along that path, right? Suppose that this question is given. So how to solve this question? See, we know heat capacity along any path C is equal to CV plus R by 1 minus N, right? And the path is given P by V is equal to constant K. So we can write PV to the power minus 1 is equal to K. So N is equal to minus 1. N is equal to minus 1, right? Put here N is equal to minus 1, right? And put here value of CV. Monoatomic, so CV is equal to 3 by 2R. 3 by 2R. So this is equal to 3 by 2R plus R by 1 minus 1. So this is equal to 3 by 2 R plus R by 2. R by 2, right? So this is what? 4R by 2 means 2R. So this is the answer, right? So the heat capacity along that path you can calculate very easily, right? Good. Well, see, there is one question. Suppose that this a gas, ideal gas is given 1 mole, 6 dmq, 27 degrees Celsius. This is the initial state of the system, and it reversibly and adiabatically, volume is decreasing. So compressed, basically compressed to this volume. Temperature you have to find out. So this is the crucial point to solve such questions, right? And CV is given for the gas. Find work, heat, delta E and delta H. So see, first point, the process is adiabatic. So the heat change, right? Answer. The heat change delta Q is equal to 0, right? Delta W, delta Q. Okay, so delta Q is equal to 0. There is no heat change between system and surrounding. Now the main point is how to calculate this temperature. This process is reversible. So if the process is reversible, so we have formula T1 V1 to the power R by CV is equal to T2 V2 to the power R by C. This formula we have already derived. You can see, I mean, your notebook. In your notebook, definitely this is written. So put the value. Initial temperature 300 Kelvin, 300 Kelvin, and 6 dm cube, 6 dm cube to the power R by CV is equal to T2. We have to find out, and 2 dm cube to the power R by CV. Very simple. Now T2 is equal to 300 Kelvin and 6 by 2, 6 by 2 to the power R by CV. So this is equal to 300 Kelvin and 3 to the power R is 8.314 joules per mole. Excuse me, divided by CV. CV is given 20.91, 20.91 joules per Kelvin per mole. Joules per Kelvin per mole. Right? So this is cancelled. So we can write 8.314 divided by 20.91 0.397. So this is 300 Kelvin 3 to the power 0.397. 397. So this you can solve this, and you will get this is equal to 464.3 Kelvin. So you have now achieved the task. If you have calculated temperature, final temperature, then your task is over. Now delta Q 0, and now delta E is equal to NCV delta T, NCV delta T, N is equal to 1 mole, CV is equal to 20.91 joules per mole per degree Kelvin, and delta T is 464.3 minus 300, right? So this is equal to mole, and this is Kelvin. So this is joules. So 464.3 minus 300 is equal to 164. 20.91 into 164.3, this is joules. So multiplied by 20.91, this is equal to 3435. 3435 joules, right? So this is delta E, and work delta W is equal to minus of delta E. This is from the first law of thermodynamics. Delta E is equal to delta Q plus delta W. This is equal to 0. So delta E is equal to delta E is equal to delta W, W is equal to delta E, not minus E, right? So this is equal to 3435. 3435, right, joules. So work is equal to 3435 joules. PdV work and compression, yes, okay. So 3435 joules, and delta H is equal to NCP delta T, right? This is the formula. Cp is equal to R plus Cv. So this is 8.314 plus 20.91 joules per Kelvin per mole, right? So this is equal to 1 mole, a 20.912. So this is 20.91 plus 8.314. 29.224. 29.224 joules per mole per degree Kelvin multiplied by 164.3 Kelvin. This is cancelled, this is cancelled. So multiplied by 164.3, 4801.5 joules. So say delta E is equal to 3435 joules. Delta H is equal to 4801.5 joules, and delta W is equal to 3435 joules, and delta Q is equal to 0. So see, this is the answer, right? So in this way we can calculate the work, heat, and change in internal energy, change in enthalpy for adiabatic reversible process in this question, right? So hopefully it is clear to all of you. There should be no problem, right?